Hello, everyone. My name is Ryan Bushy, the digital editor for Drug Discovery and Development, and I'd like to welcome everybody to today's webinar brought to you by Capsigal. The title of today's presentation is called Multicomponent Amorphous Solid Dispersion Systems for Bioavailability Enhancement. A large fraction of new chemical entities require solubilized formulations to achieve efficacious oral exposure. Amorphous solid dispersions, typically made by hot melt extrusion or spray drying, increase dissolution rate and supersaturated concentrations of these insoluble compounds in the gastrointestinal tract, which often translates to rapid absorption and improved bioavailability. Our experts today will discuss spray-dried dispersion-based formulations of low-solubility compounds, multi-component amorphous formulations, and the design of multi-component amorphous compositions and architectures and achieving manufacturability. While you are listening to the presentation today, I'd like to encourage everyone to submit questions at any time by typing into the designated comment section on the bottom of your screen. Following the presentation, we will have a question and answer segment where today's speakers will answer individual questions submitted by members of the audience. Remember that today's webinar will also be available on demand, so you can view it again at your convenience or share it with friends and colleagues. You will receive an email with a link to access the webinar within the next few days. Now I'd like to welcome today's speaker. Kim Shepard is a senior engineer at Bend Research, where she works on internal research and development initiatives to improve understanding of multi-component amorphous formulations, spray drying, and atomization. Kim has worked with Bend Research since 2015. She graduated with a PhD in chemical engineering from Princeton, focusing on the physics of amorphous materials and thermal properties of polymers. I'm now going to turn it over to our speaker for the presentation. Enjoy the webinar, everyone.
Thank you very much, Ryan. And thank you all for joining me today. So first off, I will be taking you through the motivation for this work, namely the need for bioavailability enhancement in low-solubility compounds. We'll discuss how spray-dried dispersions have been used successfully for solubility enhancement of a wide range of APIs. And then I'll take you through some case studies in which we used multi-component amorphous systems to formulate a range of challenging compounds. A majority of drug candidates fall into BCS class 2 or 4, meaning that they have low solubility, which hinders their bioavailability in vivo. So the need for appropriate solubility-enhancing technologies is a significant growth area over the past couple of years. Due to this high interest in solubilization-enhancing technologies, there's been significant progress in this area, and that's led to a lot of options for formulation. If you want to read through a really thorough review of this topic, allow me to recommend my colleague, Dr. Williams' paper, which is cited below. I've compiled here a brief summary of the techniques in this graphic. The strategies for solubilization range from dissolution-based technologies, such as lipid formulation or cyclodextrin complexation, to trapping the drug molecule in a high-energy state, like for a polymorph or an amorphous dispersion. Selecting an appropriate technology for a given molecule can be guided based on the properties of the drug, and it's also important to take into account the projected dose for the drug, as well as the product concept and intended dosage form. This is one example of the kind of two-dimensional guidance maps that we use at Capsigal Bend to identify appropriate solubilization techniques for a molecule. So in this case, both compound aqueous solubility and lipophilicity act as guiding parameters. Near the top of the chart are the highest solubility compounds, which don't need much help, and they could be formulated in the crystalline state. APIs with slightly lower solubility can achieve good absorption when formulated as nanocrystals. For progressively lower solubility, more lipophilic compounds, an amorphous formulation can be enabling. Note that amorphous formulations are appropriate for compounds spanning many orders of magnitude in both solubility and lipophilicity. The most lipophilic compounds benefit from a lipid or SEDS formulation. In this webinar, we'll be particularly focusing on solubility enhancement via the amorphous state. I've put a few markers on this chart, the little gold stars, for the 3 model compounds that we'll be discussing today. 2 of them fall right in the heart of the amorphous formulation region, and 1 is actually down below that in the gray area that's marked as a challenging formulation space. There aren't too many compounds with ultra-low solubility that manage to progress to the development phase, but this could potentially change in the future. The main idea for amorphous solubility enhancement is that a drug in the amorphous state has a higher free energy than the corresponding crystalline polymorph, and therefore has a higher solubility. In the many compounds that we've screened internally, we've observed amorphous solubility enhancements ranging from 2-fold up to 150-fold. A typical amorphous enhancement is around an order of magnitude. The amorphous solubility itself is fairly straightforward to measure in the lab. When we do this, we use a UV probe dissolution apparatus to determine the maximum concentration of dissolved drug that can remain in solution. The way we introduce amorphous drug to the media is that we use a syringe pump, and that gradually adds a concentrated drug solution in an organic solvent. The UV probe then monitors the concentration as drug is added. When we exceed the amorphous solubility, solid or liquid drug-rich phases will begin to phase separate out of the media, and the UV probe picks that up by detecting a scattering signal, as you can see in this plot above. The onset of that scattering event is defined as the amorphous solubility for this system. This test can help us to learn about how well the compound can be solubilized before we have to manufacture any amorphous dispersions, and this test can be done with just a few milligrams of compound. So this is ideal for very early development stages. Learn as much as you can about the compound. You can also conduct this amorphous solubility test with concentration-enhancing polymers in the media, and that can be used to screen which polymers are going to interact positively with the drug by increasing sustainment or preventing crystallization. And I've shown an example of a polymer screening experiment on the next slide. In this example, we have Erlotinib, and that's one of our model compounds that we'll be talking about. The black curves here are the amorphous solubility test curve in simulated intestinal media, and the red curves is the same drug in the same media with the inclusion of a small amount of a sustaining polymer, that's HPMC, that's added to the mix. And you can see from this plot that the HPMC channel sustained for quite a bit longer than the ones without it. So before doing any kind of formulation work, we already know that HPMC is a good polymer to use for Erlotinib if we are interested in delaying crystallization. It's important to keep in mind that the amorphous state itself is metastable, meaning that no matter what, the drug always has some driving force to revert back to the crystalline state. However, inclusion of these sustaining polymers can help prevent crystallization from occurring on timescales that are relevant to drug absorption. And this plot on the right are examples of this. The green curve is a typical dissolution curve for crystalline drug, which dissolves straight up to its crystalline solubility and stays there. The dotted black line shows an example of an amorphous formulation which dissolves up above its crystalline solubility, but then begins to crystallize out of solution. You can see that drop in the line. The pink line, on the other hand, shows an amorphous formulation which is able to sustain a concentration well above its crystalline solubility. So we would call this an amorphous formulation which sustains well in the dissolution test. The graph on the left describes the speciation of the drug in solution at different doses. For a dose below the crystalline solubility, the solution is thermodynamically stable. However, when the dose falls below the amorphous solubility but above the crystalline solubility, your solution is now going to be metastable because it's supersaturated. For a dose for concentration that exceeds the amorphous solubility, drug was going to be molecularly dissolved in the media up to the amorphous solubility, and then the remainder of that concentration will go into either colloidal species or undissolved solids. So that's essentially a phase-separated system, like we saw using the UV probe. When they're small, colloidal species can be useful for bioavailability enhancement. When the dissolved drug is absorbed in vivo, colloids can act as a fast-dissolving source of more free drug. And oftentimes, it's useful to formulate with colloid formation as a goal for dissolution. The these past few slides have motivated why amorphous formulations are useful, and now I'm going to discuss a little bit about how we manufacture them. One way of manufacturing solid amorphous dispersions is by spray drying. The drug and a dispersion polymer are dissolved in an organic solvent, and this solution is then atomized through a spray nozzle to form droplets. The droplets are rapidly dried by hot drying gas, forming amorphous SDD particles. These particles have been rapidly cooled and dried so that the drug and polymer are trapped in the amorphous state. This picture below shows a typical SDD raisin-like morphology. The resulting SDD, spray-dried dispersion, is a single-phase stabilized amorphous dispersion. One of the most important properties of an SDD is the glass transition temperature, or I'll call that the TG throughout this presentation. On heating up to the glass transition temperature, the material is going to soften as its disordered molecules begin to gain mobility. Above the TG, the dispersion will be a liquid, and the drug then has the potential to crystallize. The TG is a crucial property for determining the physical stability of an amorphous material. The kinds of dispersion polymers that we typically use for spray drying fall into two categories. Enteric ionizable polymers are not ionized at gastric pH and therefore resist dissolution in the stomach. They also resist the uptake of water in the solid state when the polymer is protonated and therefore hydrophobic. This means an enteric dispersion's TG will not be depressed as much by exposure to high humidity. This is very important for good physical stability. Neutral polymers, on the other hand, are helpful for applications where we might desire dissolution in the stomach, or when chemical interactions between the API and an acidic polymer make the use of an enteric polymer impossible. There are many possible polymers for use in SDDs, but here's four of the most common ones. HPMCAS, which is hydroxypropylmethylcellulose acetate succinate, is one of the most common dispersion polymers that we use. There's a lot of things going for it. It has a fairly high TG. It's amphiphilic, so it nicely balances dissolution rate and sustainment. It's tolerated well by the body and is available in 3 different compendial grades, which I'll discuss shortly on the next slide. Oidrogate L100, which is a methacrylic acid copolymer, is another enteric polymer option. It has an even higher TG than HPMCAS and even lower water uptake. It has a quite fast dissolution rate in intestinal pH media, but often suffers from poor sustainment. We'll talk more about that later in this presentation. PVPVA is a neutral copolymer with high solubility in aqueous and organic solvents. It has a fast dissolution rate at any physiological pH, but it can have issues with water absorption in the solid state that can lower its TG or cause physical stability issues. HPMC is a natural cellulosic that excels at sustaining supersaturation in amorphous formulations. As a dispersion polymer, it can have difficulties with dissolution rate, and we'll be talking about this polymer quite a bit in the second case study that we'll cover today. So there are 3 commercially available grades of HPMCAS polymer, which have different side group substitutions that make them each perform differently. HPMCAS-L has more of the hydrophilic succinyl side groups. That gives it the fastest dissolution rate in aqueous media of these 3 grades, but the least sustaining power. HPMCAS-H has more acetyl groups and is therefore more hydrophobic. It's good for sustainment, can have slow dissolution rate. HPMCAS-M is intermediate in its properties. And the different performance of these 3 HPMCAS grades will come into play in our first case study. Over the past 2 decades, we've had great success at Capsugel Bend, formulating over 1,000 compounds as spray-dried dispersions. The APIs that we've formulated have a wide range of physical properties, and that's shown here on this plot of Tm divided by Tg versus log P. In these systems, we use only the drug and choose 1 dispersion polymer, so that's only 2 components. For the vast majority of compounds, we've been able to keep these formulations very simple, making what we would call a binary SDD. But what defines a successful SDD? Performance, stability, and manufacturability are all key. For example, nobody can use a formulation that's manufacturable if it doesn't perform well or is unstable and can't be stored. Any formulation that works well and is stable is just a dream unless it's manufacturable. So here we break down these requirements a little bit farther. In the performance category, we have rapid dissolution rate as well as sustainment. On the stability side, we differentiate between chemical and physical stability. And I mentioned before that when possible, we like to keep the formulation simple. But sometimes we encounter situations where we're unable to meet all of these success metrics in a binary formulation, and we're not willing to compromise. So these are the situations where a multi-component formulation comes into play. The goal is to essentially divide the labor of the formulation by choosing multiple excipients, each with a particular performance requirement in mind. So today my case studies will cover just performance, particularly the balance between dissolution rate and sustainment. Here's what a multi-component SDD system can look like. Here we're specifically addressing the problem where we need to balance fast dissolution rate with good sustainment. There are three basic architectures that we can use to incorporate a third component into our system. The first architecture is the simple one. We take a binary SDD, which dissolves quickly, and pair it with a sustaining polymer, simply blending the two together. This can be formulated into any standard solid dosage form, such as a tablet or a capsule. In architecture number 2, we use a VCAPS Plus, which is an HPMC-based capsule, and that is the source of the sustaining polymer for the system. The SDD contained inside the capsule is a standard binary SDD. This architecture is really convenient for formulating since you don't need any additional formulation steps beyond the binary SDD manufacture. In the third architecture, the ternary SDD is formulated, and that contains all three of the components that we want in the same SDD particle all sprayed together. The SDD can then be formulated as needed into a final dosage form. And this brings us to our first case study. Itraconazole is an ultra-low solubility compound, occupying that gray space on our formulation map that I mentioned before. Itracanazole's solubility in simulated intestinal media is only 70 nanograms per milliliter. And that would be solubilized primarily in the bile salt micelles that are present in simulated intestinal media. So there's almost no molecular solubility of this drug whatsoever. So our problem statement is essentially entirely solubilization enhancement. Now, when we do the amorphous solubility test, we find that it has up to 7 micrograms per mil amorphous solubility. And that's actually a huge amorphous enhancement of 100-fold. However, 7 micrograms per mil is still not actually sufficient for dosing in vivo. So the majority of solubilized species in a dissolution test aren't molecularly dissolved. They're drug polymer colloids that are typically 200 to 400 nanometers in diameter. We know that smaller colloids diffuse faster through the mucus boundary layer in the intestine, proportional to the inverse of their radius. So the goal for itraconazole is to formulate to maximize the amount of these small colloids using an SDD. Before I dive into the data here, let me tell you a little bit about the details of how we did our dissolution test. So the procedure is essentially that in this test, which starts in intestinal media, we pull small media aliquots that are microcentrifuged at 15,800 G for 1 minute, and those remove just the coarse particles in the formulation. Small colloids are going to remain in the supernatant, and we then analyze the concentration of that supernatant via HPLC. So this technique of separation is just a coarse way of determining the concentration of species that are small enough to be active in vivo, but it's not a hard cutoff. On the right, you see the results of that material-sparing dissolution test, where we have SDDs formulated with the 3 different grades of HPMCAS. And what we can see here is that in red, the HPMCAS-H SDD doesn't have a very good dissolution rate. but it doesn't have a problem with sustainment. On the other hand, the more hydrophilic grades of HPMCAS have very good dissolution rate, but poor sustainment. So the decrease in concentration that we're seeing in this dissolution test is the colloids are actually coarsening or growing in size, and therefore they spin down in the microcentrifuge. We don't observe any crystallization issues for this system. So this brings up the question of, if we can formulate with the best of both worlds, meaning the advantage of the HPMCAS-H and of the HPMCAS-L, maybe then we can achieve a good balance of sustainment and dissolution rate. Here we're using an example of the first architecture where a sustaining HPMCAS-H particle is blended with a fast-dissolving SDD made of Itraconazole and HPMCAS-L. In this dissolution test, we performed a gastric to intestinal transfer test, which begins with 30 minutes of gastric exposure in pH 2 media. That's followed by a 1-to-1 dilution to pH 6.5 with a 6.7 millimolar sodium taurocholate simulated intestinal media. And it's clear from this dissolution test that the presence of this sustaining polymer significantly helps to maintain a higher concentration for the dissolution test. Now, the reason for this, we can see in the plot on the right, this is some DLS data that tells us the particle size of those colloids versus time in the dissolution test. And what you can see is that the HPMCAS-L with H colloids start smaller and they stay smaller. So that tells us that the presence of this more hydrophobic polymer is stabilizing the colloids, and that's what's able to keep them in solution for longer during the dissolution test. So we can take the ternary blend on the previous slide and formulate it as either a tablet or a capsule, and we can see quite similar performance. In general, while we're developing a formulation, we regard the performance of the SDD suspension as the best case scenario, where we can't do too much better than that. So we're often looking for if we can achieve equivalent performance with a solid dosage form. Here, making the solid dosage form is pretty straightforward. We blend, then granulate the first architecture and press that into a solid dosage form, and either one of them achieves rapid dissolution and long sustainment. To briefly summarize this Itraconazole case study, in general, the problem statement for Itraconazole is that we need to solubilize an ultra-low solubility compound. And the majority of that solubilization is achieved via colloid formation. So we use a multi-component approach to divide the labor using the HPMCAS SDD to provide a fast dissolution rate, and external HPMCAS-H is able to help sustain the colloids to prevent them from growing in diameter too quickly and falling out of solution. Ternary Itraconazole solid dosage forms can be prepared as either a tablet or a capsule and have equivalently excellent performance as the SDD powder. We've gotten to our second case study, and that's Erlotinib. So Erlotinib is a basic compound that has moderate solubility in gastric media, but crystallizes out of solution at higher pH. Our goal is to enable it to sustain supersaturation longer at intestinal pH. This is a fairly common problem statement for weakly basic drugs, which are becoming increasingly popular. Again, the strategy here is to employ a sustaining polymer alongside a fast-dissolving dispersion polymer. In this case, we chose HPMC, which should sound familiar to you, because it's been shown in our amorphous solubility test that it can help inhibit crystallization in this system, but also in many other similar weakly basic systems. We tested all three architectures for this particular case study and found them all to be successful with different advantages for each of them. Here's an example of the first architecture where we use the Oidrigit L100 Erlotinib SDD and co-dose that with HPMC. This dissolution test is again a gastric to intestinal transfer test with 30 minutes of pre-exposure in gastric. However, instead, the concentration here is monitored by a UV probe rather than by HPLC. On the right side, you can see that the SDD that's dosed with HPMC is effective even at very small amounts of HPMC. The lowest effective amount that we managed to test was just 50 micrograms per milliliter in the media. So let me walk you through this disso. The blue curve is our control system, where we don't have any sustaining polymer present. You can see that crystallizes out of solution very rapidly after the transfer to intestinal media. It begins to crystallize within 90 seconds. On the other hand, as soon as we add any HPMC to the system, we see a huge increase in the time to crystallization, the AUC, and the Cmax, starting with that 50 micrograms per mil. And you can get slightly better performance with increasing amounts of HPMC. However, you kind of hit a wall of diminishing returns after about 200 micrograms per mil. However, adding a lot of HPMC isn't deleterious to the system. It still performs well, it just doesn't perform better. So this says we have a lot of flexibility with the kind of concentrations that we formulate with, and that you don't need much to see any kind of an effect. On the bottom here, I have two polarized light microscopy images. And on the left is the precipitate taken from the control channel at the end of the dissolution test. So you can see from this that there's quite a bit of birefringence in the image, indicating that the precipitate is crystalline for the control system. On the right image, this is taken from one of the systems that contained HPMC, and the precipitate here looks very different. It's larger, it has a network structure with pretty much no birefringence, indicating that it is not a crystalline precipitate. We also confirmed that using the spectrum of the UV probe. The amorphous and crystalline precipitate do have different UV spectra. So what's happening is the HPMC is interacting with the drug in such a way that it is changing how the drug precipitates out of the media. Here's an example of architecture number 2, where we used a binary SDD encapsulated in VCAPS+. That's the sustaining capsule made of HPMC. This architecture is really convenient because all you need to do to increase the formulation sustainment is put it in a VCAPS+ instead of a gelatin capsule. So in this dissolution test, it's clear that the results for the VCAPS+ greatly outperform that of the gelatin capsule. It enables longer sustainment, similar to our previous architecture, a higher Cmax in this case, and much higher AUC. This approach, formulating in a VCAPS+ to get increased performance, is also quite general with weakly basic compounds. Itraconazole is a model weakly basic compound which quickly crystallizes during this gastric to intestinal transfer test shown in the top left. When ketoconazole is put in a VCAPS+, shown in the top left here, the sustainment is again extended significantly. The same is also true for dipyridamole, shown in the bottom left. And this effect has been demonstrated in the literature for a third weak base, dabrafenib. I've reprinted some of the key findings here. On the bottom right is an in vitro dissolution test that demonstrates that crystalline dabrafenib loaded into an HPMC capsule has a higher Cmax and AUC than that in a gelatin capsule. In the top right figure, the dabrafenib was then dosed in a clinical trial where the HPMC capsule also significantly outperformed the gelatin capsule. So overall, we see that HPMC is a powerful sustaining polymer. VCAPS+ is a simple way to introduce that sustaining polymer to your system for a variety of weakly basic compounds. In the third geometry, we have all three of the components for the multi-component formulation are sprayed into one SDD particle. And this architecture has some interesting enhancements. On the right side of this gastric to intestinal transfer test, we can see that the ternary SDDs achieve similar performance to that of the other architectures. We have our enhanced sustainment, higher Cmax, and higher AUC. However, we also see some interesting differences on the left-hand side. So in the gastric portion of the test, we have a combination of an enteric and a non-enteric polymer inside this SDD. So by changing the HPMC content inside the SDD, you can directly tune the amount of gastric release that is achieved in the gastric portion of the test. So that's convenient to be able to have tunable gastric release without sacrificing any of the sustainment in the intestinal portion of the test. Let's summarize the Erlotinib case study. In the case of Erlotinib binary SDDs, they crystallize immediately after they'll dissolve to a fairly high extent in gastric media, but then they'll crystallize immediately in intestinal pH media. So we have three architectures that help us to introduce a sustaining excipient. We have external, in which we blend the excipient with a binary SDD. We have using the dosage form, meaning an HPMC V capsule, or incorporating all three components in a ternary SDD. And all three of these architectures have been shown to increase AUC in intestinal media by at least 10-fold. All right, this brings us to our third case study. And for this particular case study, we needed to keep the drug anonymous for client confidentiality reasons. So for compound X, it's a large lipophilic molecule that is also weakly basic. We know that it doesn't crystallize out of solution in our experiments, and it has a typical amorphous solubility enhancement of approximately 20-fold. So to improve the bioavailability for this compound, we want to maximize its breakup into solubilized species while it's still in the gastric portion of the test, or in vivo while it's still in the stomach. We hope to achieve high free drug, high amounts of drug and surfactant micelles, and high levels of colloids to balance this out. To encourage colloid formation in the gastric portion of the test, we incorporated a surfactant, TPGS, structure is shown here on the slide, into the SDD itself, forming a ternary SDD. The TPGS aids in phase separation of the SDD, and it helps to stabilize the resulting drug-rich colloids. So the cartoon shown here gives a schematic of how an SDD is able to phase separate to form colloids. The dry SDD, pictured below, swells and hydrates when it's placed in aqueous media. So we have the cartoon schematic up on the top that shows approximately what's happening as the SDD swells, and then we also have FDM and optical microscopy images that show this gradual hydration of the outside layer of the SDD. So as the water enters into the SDD, the lipophilic drug has a driving force to phase separate from the more hydrophilic polymer. And the surfactant can help to stabilize the resulting phase-separated colloids at a small size. There are two TEM images here, one of which on the bottom right is a little easier to see because it's zoomed in. But this is what we're able to see when these phase-separated drug-rich nanostructures can form within an SDD. When the polymer fully dissolves, the drug colloids are then released into the media as is schematically dictated in this upper right part of the cartoon. Here's an example of the dissolution of an SDD that's been formulated with and without TPGS in it. The green lines represent the composition of the control SDD, which doesn't contain any TPGS. So we have another gastric to intestinal transfer test here, where the aliquots are acquired by HPLC. In this particular case, the free drug measurements are taken by ultracentrifuge, where all of the colloids are spun down out of the system, and the colloid plus free drug plus micelles aliquots are taken via a filter. The dotted lines represent the free drug concentration, so that's the ultracentrifuge concentration, and the solid line is the concentration of free drug plus micelles if they're present, plus colloids. You can see from this plot that not much of the drug is solubilized in colloidal form for the control SDD. However, for the TPGS containing SDD, and that's shown in red here, the solid line is about 2 times higher than the dotted line. And that indicates that about half of the solubilized drug is in the colloidal form. You can see the same thing in the bar graph on the right that's taken from, I think, the negative 15-minute time point during this dissolution test. You can see the comparison between the free drug and the colloids is quite striking between the control SDD and the TPGS. So the inclusion of TPGS inside the SDD greatly improves the SDD's ability to form colloids, and it has the added bonus of a little extra micellar solubilization. On the left-hand graph here, that's just reproduced from the previous slide. This represents a 25% active loading. On the right is an analogous set of formulations at a 10% active loading, with and without TPGS. So we can see in this right-hand graph that when you're able to lower the active loading so significantly, TPGS isn't needed for colloids to form, since the control SDD forms a similar amount of colloidal species. However, if you're interested in maintaining a high active loading or increasing it beyond this 10% active, adding TPGS to a system like this is quite helpful for maximizing loading. The 25% loading with TPGS has much more similar performance to the 10% loading than to the control. So that shows that the inclusion of TPGS can be helpful in situations where maximizing the active loading is critical. To briefly summarize this case study, the formation and sustainment of drugs solubilized in colloids is done using surfactant. A higher loading SDD formulation with TPGS is going to perform similarly to a much lower loading formulation without it. That means that TPGS inclusion is a really helpful way to enable us to increase the loading in the formulation, which is often of very high priority. And this brings me to the end of what I wanted to talk about today, so I'll go through a couple of take-home points with you. Spray dry dispersions are a well-developed technology, a precedented enabling technology, and has a really wide range of applicability across different ranges of API characteristics. Ternary systems help us to expand this application space for the spray drying technology. Our general strategy for a multi-component SDD is to divide the work. When a binary SDD can't meet all of the requirements and we can't make compromises, a multi-component system can help you out. When we pair a fast-dissolving SDD with a sustaining polymer, we can formulate that as a ternary SDD, a sustaining capsule, or an external blend. Those are all possible architectures, and they have different advantages and disadvantages. Surfactants are able to help improve the dissolution rate for systems with sufficient sustainment. And the key in our design is the speciation, so what kind of drug species are formed during a dissolution test. The drug can be solubilized in micelles as neutral or ionized species, or in drug-rich colloids, and different excipients are going to help you dictate that speciation in different ways that you can help target what you need to make your formulation succeed. So thanks for joining me, and I'm excited to answer all of your questions.
So thank you for your presentation, Kim. We're now taking questions on today's webinar. I'd like to remind and encourage everyone to submit questions at any time by typing into the space provided on your screen. All questions that are not discussed in the Q&A segment will be answered by representatives of Capsugel at a later time. So let's get started. The first question we have here is, Kim, you talked about using ternary architectures to balance dissolution rate and drug sustainment. Are there any applications where you balance other requirements, i.e. stability or manufacturability, with each other or against a performance metric?
Good question, thanks. So absolutely, even though we didn't have time to cover it today, balancing all of the performance metrics is obviously going to be important. Chemical stability is a good example. For some APIs, chemical stability with an acidic polymer like HPMCAS is not going to be beneficial, meaning that we need to use a neutral polymer like PBPBA in the SDD. However, the PBPBA would be unlikely to sustain well enough. So if you incorporate an external sustaining polymer, we might be able to fix the poor sustainment of the PBPBA, the neutral polymer, and that wouldn't compromise chemical stability because your sustaining polymer could be external to the SDD.
All right. So our next question is there any correlation between the solid state stability and the stability in supersaturated solutions? HPMCAS systems, for example.
So that's probably a case where the architecture is fairly important because it's true that the solid state stability and the stability in supersaturated solution are kind of two different problem statements that occasionally become intertwined. So the solid state stability, at least from the perspective of physical stability, is going to be predominantly dictated by the glass transition temperature and by the mobility in the system. So if you're using an external geometry where you don't add any of the sustaining polymer into the SDD, that wouldn't affect the solid state stability. But for cases where you're incorporating something into the SDD, then those problems become coupled because usually your two polymers are going to have different TGs and therefore going to have different mobilities. But it's not that adding HPMC just magically fixes both of those problems. The mechanisms are going to be very different. One is a mobility-based mechanism and one is a polymer-drug interaction mechanism. That's a really good question.
Interesting. So our next question, for the Itraconazole case study, you only use an external architecture. Why not make a ternary SDD of Itraconazole with HPMCASL and HPMCAS-H to get fast dissolution and good sustainment?
So we actually put a fair amount of work into testing this hypothesis because it seems like it would be a pretty convenient answer to making an easily manufacturable system. But what we see is that when we put the hydrophilic polymer, the hydrophobic polymer, and the itraconazole all into the same SDD, the lipophilic drug tends to associate itself with the HPMCAS portion of the matrix because it's also more lipophilic. So because of this, the drug has that kind of characteristic poor dissolution rate that's similar to a binary HPMCAS-H SDD. So rather than getting the best of both worlds, we're kind of getting the worst of both worlds. These lipophilic domains, they tend to aggregate, and then you don't get any colloids. So we even tried fairly low loadings of HPMCAS-H, and we still found this to be the case. So this is an example where not all of the architectures worked. So that's where maybe you need to rationally choose which architecture is going to be best suited to what you need.
But then how would you design a multi-component system, and do you follow a decision tree?
Yeah, so in this case, that would mean that we're going to need to pursue one of the two external architectures. So there is, to some extent, there is a decision tree that we're starting to develop. But for the case of something like this, we can tell a little bit by the drug properties whether it's going to be more likely to require an internal or an external architecture. Itraconazole is probably one of the tougher cases in particular.
So could you use this technology for formulating a metastable polymorph of an API?
Well, if you have some excipients that are able to help you encourage forming this higher energy polymorph, I would say that's certainly possible. I haven't worked with that particular problem statement. We're generally trying to get things to be stable in the amorphous form rather into higher energy polymorphs. But if you had a specific drug-polymer interaction, I could see how that would be possible.
So then how thermally stable must the drug be to make SDD feasible?
Well, it depends a lot on what your goals are for the formulation. Generally, we're looking for something that's going to pass our standard stability conditions, so something that can be stored at room temperature at moderate humidity. So how thermally stable that would need to be, you probably need to have its glass transition temperature be at least 15 to 20 degrees above its storage conditions to keep the mobility low. And for systems where you're adding a low TG surfactant, that can be an important consideration that may limit the loading of surfactant that you're going to use. So that's sort of the rule of thumb we use. However, we have had systems that didn't need quite as stringent of requirements.
Gotcha. So could you extend the chemical stability of amorphous materials and APIs?
So depending on what the interactions between the excipients and that API are going to be, that could be helpful. There's lots of cases where you might design a system that includes a third component where you're deliberately including, say, an antioxidant, or maybe you're formulating in such a way to insulate your API from exposure to oxygen or light. So there are ways to use a ternary system to achieve chemical stability goals, even though we didn't cover those in detail today. That's definitely possible.
Now, what are some of the deciding factors when choosing which multi-component architecture to evaluate, ternary or externally?
This is a good question, and this will probably, I can answer based on what we talked about a little bit earlier. So for some applications, the mechanism of how the SDD dissolves is going to tell you what architecture you need to use. And we talked about today the example of drug X and TPGS in a PV-PVA dispersion. The TPGS wouldn't have been effective externally in this case because the phase separation is generated inside the SDD particles, not outside. So in the Itraconazole case study, an external architecture was actually needed because, like I mentioned before, when we made that ternary SDD using both grades of HPMCAS, even a little bit of H caused the SDD's dissolution rate to decrease. So in that case, the lipophilic drug was associated with lipophilic polymer. Other times the architecture is flexible, so then it can be chosen for whatever is simplest or most appropriate or even most convenient for your formulation goals. External architectures are helpful for quick screening in early development, but using a sustaining capsule might be more convenient because the control material can be used to directly test the formulation. Other times, ternary SDD is going to be more appropriate because it eliminates the blending or refilling step. The Erlotinib case study is an example where you do have that sort of flexibility. So overall, you look at what your goals are for the formulation, you look at what your hypothesis is for how your formulation is going to be improved by that component, and then you decide that way.
So then do you think the strategies that you illustrated can be used to formulate a composition containing two molecules that are not compatible, reacting when in touch?
That's a really good question because that's a really big problem statement for a lot of drugs that are under development right now. And that's a challenging one. That might be an example where you would use more than a ternary system. That might be an example where you design one SDD of one of the drugs with whatever necessary excipients and another SDD of the other drug with whatever necessary excipients, and use those excipients in a rational way to help isolate the drugs from becoming too intimately mixed and having chemical stability problems. I don't think a ternary system is a magic bullet for that problem statement, but I think there are definitely ways that it could be applied to help.
Great. So have you identified any para-IV opportunities using technology?
Not that I'm aware of, but that's not something that I typically work on. All
right. So our next question, in all cases you have taken physical mixtures of drugs and polymers. You haven't considered drug-polymer interactions which may improve the solubility and help in sustainment. Can you comment on that?
Sure. So technologies like complexation are definitely a valuable way of looking at this. And the amorphous solubility test might be a good way to screen for that because you can take into account very specific interactions between a drug and an excipient and screen them in a high throughput way without using large amounts of API or excipient. So that's not something that we were attempting to do on this particular project. We were aiming for more broadly applicable solutions, but it's absolutely important for a lot of systems to develop the kind of knowledge of really specific interactions like you're saying, absolutely.
All right. So our next question, have you tried this technology for co-crystal so far?
No, we haven't, and that's a really interesting problem statement that would probably be something we'd be interested in looking at. We haven't tried it yet.
Okay. So are the ternary architectures applicable to formulations besides SDDS, i.e. HME, lipid formulations, crystalline drugs?
Sure. I would say so, though for using other kinds of amorphous formulations or other kinds of solubility enhancing formulations, some of the details would differ, but the concept of introducing functional excipients is definitely applicable to many types of dosage forms. I can speak from experience, at least on crystalline drugs. We have tested the applicability of VCAPS Plus to sustain crystalline formulations of a variety of weekly basic drugs, and we found that that can be fairly effective. In HME, so that's hot melt extrusion, excipients like TPGS are very commonly used to improve manufacturability because they lower the TG and therefore make it easier to process at high temperature. And that could certainly have a positive impact on performance, and I know that people who work in that area probably know a lot more about these low molecular weight excipients than I do.
Great. So our last question is, how do you stabilize colloids dispersion made with a surfactant and ensure it doesn't change back to a crystalline state?
So that's a big question about whether surfactants specifically can be used to stabilize colloids. In our experience, we've had better luck with using a higher molecular weight material to sustain colloids, like our HPMC polymer or our HPMCAS-H polymer. We haven't had quite as much success using surfactants. However, the TPGS in this case, we think that it's kind of similar to a paper in the literature by Paul Harmon, where the TPGS is able to surface functionalize the colloid at a smaller size, and once the TPGS can fully coat the surface of the colloid, then you no longer see the colloids growing in size. It's a really interesting explanation in the literature, and that's to the best of our knowledge.
All right. Well, that is all the time we have, so that was our final question for this section.
Thank you.
So I want to thank everybody for attending, and that concludes our webinar for today. Thank you to our exceptional speaker, Kim Shepard, and our sponsor, Capsigal. Look out for an email with a link to access this webinar on demand within the next couple days. As always, have a great day.
Thank you.
Thank you, everybody.